student of Dorothy Hodgkin's, couldn't quite cut it as a crystallographer, but for some people, you haven't found your true thing, and she was able to find another job, so I'm told. So just remember that if you're not good at one thing, there's something else out there that you might be good at. So let me give you a second example of a chelate. This molecule is known as EDTA. So this ligand has 6 points that it can attach to a metal. So it has 6 atoms that can serve as these donor ligands. So we have one up here, we have the little electrons and the oxygen, another oxygen down here, nitrogen, nitrogen, another oxygen, another oxygen. So all of those 6 points can coordinate to a metal. So here again is the free EDTA, and here's a structure of EDTA bound to a metal. The metal is abbreviated M. So why don't you tell me what the geometry is of that metal? All right, let's take only 10 more seconds. Hoping for 90, we're getting close, maybe by the end of today. All right, yeah, so it's octahedral geometry. So we have upper ligands and a lower ligand, 2 ligands coming out, 2 ligands going back, and it's also a hexadentate complex. So we see we're coordinated with the oxygen in red, nitrogen in blue, around to the other nitrogen in blue, other nitrogen in purple, another nitrogen up here in green and in blue. So EDTA, when EDTA binds to a metal, it forms a very stable metal complex. And the reason for this is that chelate effect and its entropy. So if we look, metals are often coordinated by waters if they're just in solution. But if you bind one molecule of EDTA to the metal, it'll take all of those 6 sites, displacing all of these 6 waters. So here, on this side, you have one thing free in solution, and over here you have 6 things that are free. So that's entropically favorable. You have more entropy when you have lots of more free things floating around. So this has greater entropy. So the chelate effect, then, has to do with an entropic effect that when you're binding a metal with multiple points of attachment, it's releasing water. So these are very stable. And so because of this stability, they have a lot of important uses. What is one use you can think of that you might have for such a thing? When might you want to chelate a metal out, get metal out of something pretty quickly? Yeah. Yeah, you can purify out a metal out of water with this. What about rushing to the emergency room with something? Yeah? Lead poisoning, yep. So sometimes you might want to just purify your water. You might be happy with that. Other times you might really want to have that metal out. So every emergency room in the United States and probably mostly around the world will have EDTA on hand in case someone comes in with lead poisoning. Do you know who's at the most risk for lead poisoning, at least in this country? Kids. And what do they do that gives them lead poisoning? Lead paint, yeah. So I don't know, most of you are probably living on campus, but if any of you move off campus, and some people who are living maybe across the river in fraternity houses, those buildings are old, and they have had lead paint in them at some point or another. So this is a big problem, actually, in the Boston area. So if you have any toddlers visiting you, you might want to make sure they're not eating paint chips off any windowsill or anything like that. Or if you do, have some EDTA on hand. All right, one other thing, some of you, once you start studying chemistry, it's always fun/scary to start reading the ingredients on food packages. But you will discover that some food that you eat will say, as an ingredient, EDTA